The COVID-19 vaccination have arrived and they are on their way across the world. Now the world faces a huge logistical challenge maintaining these vaccines in the proper storage conditions to assure the safety and efficacy of every dosage that goes into a person's arm. This is made more difficult by the fact that some of these vaccinations must be maintained frozen or refrigerated for best safety and efficacy. Because of inappropriate storage and transportations, a large percentage of food and healthcare treatments such as vaccination go to waste. It is necessary to make improvement in order to avoid the loss of expensive and valuable vaccinations along the cold chain. Providers must guarantee that they not only have the necessary equipment for this vaccination but also that they have trustworthy equipment for storing this priceless vaccine product. As a result, an ultra-cold refrigeration system with the finest function must be employed to carry vaccinations to all parts of the global without causing harm or waste. So the objective of these projects are to design an ultra-cold refrigeration system that is capable to be transported to all global locations regardless of climate change. Second, to be able to maintain the temperature of the refrigerator at -70 degrees Celsius. Third, to identify the issues when designing the refrigerator and provide solutions. And finally, to avoid a heavy financial loss to the manufacturing company and country by providing an efficient transport containers for vaccine delivery. So these are the theoretical parts. So the first one is the major design problem. Each manufacturer has a distinct dose per vial, resulting in a varied geometry of vial in which the vaccine is stored and sold in the market. The use of vaccine storage space within a vaccine carrier box is solely limited due to this geometric difference. A standard carrier box does not have an effective method for keeping vials within it. This has an impact on the vaccine carrier's performance in terms of storage capacity, storage time, and system ergonomics. Second one is the lack of storage space for an optimal weight is one of the design primary limitations. The design should have a proper stack of vaccine inside the refrigerator in order to increase the vaccine capacity and safety of the vaccine when the refrigerator is moved from one place to another place. Third one is the temperature measurement may or may not match to real vaccination temperature because the temperature monitoring device is placed as well as the time or frequency with which is data are taken. And then the vaccine storage trays or boxes can restrict refrigerator airflow, resulting either cooler or warmer air pockets. Vaccines held near the refrigerator cooling unit, for example, may be maintained substantially cooler than those kept in the refrigerator's main body. And finally, the electricity power is a major problem for a vaccine storage refrigerator. Despite this, many rural towns across the country suffer from regular power outage. So these are for the theoretical part for the maintenance. The first one is the important part is check the thermometer. Replace the batteries in the thermometer. If it is powered by batteries, check to see that the calibration certificate for the gadget has not expired. We need to check up for ice build up in freezer. A thin layer of frost does not affect the cooling performance, but a thick layer of frost negatively affects the efficiency of the system. When frost has accumulated to a thickness of 1 centimeter, the unit requires defrosting. Check the refrigerator doors seal for signs of wear on a regular basis. As a result of being old and fragile, the seal should not have any trips or fractures. There should be no gaps between the seal and the refrigerator body when the door is closed. Clean the coils and motor of the device of any dust and residue. Dust accumulation will ultimately obstruct heat transfer from the coils, causing the machines to operate inefficiently. The coils of a vaccine refrigerator are normally found in the back of the unit. Then, we need to disinfect any bacteria development, clean the units inside the cabinet and shelf. And the last one is we need to check the appliance plug to make sure it is not damaged, twisted, melted, or burnt. Make that the unit's power, cable, and all other electrical connections are in good working order, and that all wires are secure, and that there are no exposed conductors.
An ultra-low temperature ULT refrigeration is defined as a refrigeration system that operates at temperatures ranging from -50 degrees C to -100 degrees C. The ULT will require the compressor to create an extremely large pressure difference across the expansion device. So, a single compressor in the single stage compression refrigeration system is unable to achieve the ULT because of the huge compression ratios. With the growing of demands for the ULT, there are various types of cascade system, and the main type of the cascade system are, the first one are the cascade absorption refrigeration system, CARS, and the second one is the compression cascade refrigeration system, CCRS, and the third one is the compression absorption cascade refrigeration system, CACRS, and the last one is the auto cascade refrigeration system, ACRS. So for the design of our vaccine storage, we will use the CCRS, or the compression refrigeration system, to maintain the internal temperature at -70 degrees C for the vaccine. The compression cascade refrigeration system is a combination of two vapor compression refrigeration systems VCRS cycle, which is the first one is the low temperature circuit LTC, and the other one is the high temperature circuit HTC. So the both VCRL will have the common component in the VCRS, such as the compressor, a condenser, an expansion valve, and an evaporator. So the two VCRS will be thermally connected to each other via a heat exchanger that will act as the LTC evaporator and then as an HTC condenser. So the LTC will employ refrigerants with low boiling points, and on the other hand, the HTC will employ refrigerants with high boiling point. So the two distinct refrigerant of HTC and LTC is not mixed at any point in the system. And the figure beside shows the two-stage cascade refrigeration system. Refrigerants that are composed of halocarbons, hydrocarbons, inorganic compound, as well as blends of various compounds, is usually used in the application of the refrigeration system. So the selection of refrigeration for our system will be influenced by the desired output of the system and the thermodynamic properties of the refrigerant. Aside from that, the other factor that will influence the selection of the refrigerant is the environmental effects, such as the ODP, which is the ozone depletion potential, and GWP, green. The physical and chemical properties is also the factor that will affect the selection of the refrigerant. The physical and chemical properties that will be in the selection is the toxicity, combustibility, explosivity, interaction with metal materials, interaction with lubricants, and low boiling point temperature. Additionally, the critical temperature of the refrigerant should be raised while the condensation temperature should be lowered, and the critical temperature will determine whether or not the refrigerant can liquefy in the normal low temperature range. So to produce a lower temperature, the boiling point should be as low as possible. So furthermore, the refrigerant's critical pressure should be close to or slightly higher than the atmospheric pressure to increase the likelihood of air mixing into the system. So in our design, we will use the R404A as the refrigerant in HTC and R508B as refrigerant in LTC. So the table will show the property of the refrigerant selected for the HTC and LTC in our ULT system. So for the R404, the boiling point is -46 degrees C and the critical temperature is 72.12 degrees Celsius, and the critical pressure of the refrigerant is 3730 kilopascal. And for the latent heat of vaporization at boiling point, the value of the latent heat is 221.35 kilojoule per kilogram, and the ODP or the ozone depletion potential is 0. For the flammability of the R404A refrigerant, it is non-flammable, and the exposure limit for the refrigerant is 100 ppm. So for the LTC, we will use the R508B refrigerant, which has the boiling point of -88 degrees C and the critical temperature at 13.7 degrees Celsius and the critical pressure at 3935 kilopascal, and the latent heat of vaporization at boiling point is 168.4 kilojoule per kilogram, and it also has 0 ozone depletion potential. It is also non-flammable, and the exposure limit is 1000 ppm. The improvement to the system can be done to optimize the refrigeration system and also lower the internal temperature that can be achieved by the refrigeration system. So the first improvement that can be done is to increase the compressor power in the LTC to further decrease the internal temperature. So by increasing the compressor power, it will increase the mass flow rate of the refrigerant in LTC. The higher mass flow rate LTC refrigerant will extract more heat from the internal chamber, thus increasing the heat extraction rate and decreasing the temperature. The other improvement that can be done to the system is to introduce the ejector to the compression refrigeration system. The ejector is a mechanical device that uses a high pressure and velocity fluid to convey a low pressure fluid to a higher pressure fluid at a diffuser outlet. So the ejector has gained popularity in recent years due to its low cost, lack of moving part, that means low maintenance, and the ability to work safely with two-phase fluid. So the use of an ejector not only improves the cooling capacity and reduce the compressor work, but it also recover expansion process loss through isentropic expansion to improve the performance of cascade refrigeration system.
This is our vaccine container design, as you can see from the figure. Okay, the size of our vaccine container design is about 2000 millimeter times with 700 millimeter times with 1000 millimeter. Okay, this size is suitable to store a large number of vaccines since it has 3 compartments of vaccine storage. Okay, the cooling duct that supplies cool air in each compartment will supply a uniform and stable temperature distribution. It has an adjustable set point from negative 71 degrees Celsius until negative 30 degrees Celsius. Okay, then the material used for the walls and doors for the vaccine container is made of sheet metal for the core and sandwiched between an interior wall, which is made of polystyrene plastic, and an outer shell made of stainless steel. Okay, the outer shell is made of stainless steel since it can withstand any impact while in transit. Okay, then the door is insulated by seal gasket that will keep airflow accurate and enhance the frame for minimize cold air loss. The polystyrene plastic will provide high thermal insulation. Then the interior wall will be put by the antibacterial coating to prevent vaccines from contamination. These two figures show the design of our vaccine container when the door is closed and open. For the simulation of our vaccine container, okay, and SysFluent software was used to run this simulation to study the temperature control and velocity streamline of our design. Okay. As you can see from the graph of K residual, okay, we can see that the pattern of the continuity X velocity, Y velocity, Z velocity, energy, K and epsilon value decrease at iteration of 0 until 125. Okay, then the pattern increase and decrease from iteration of 126 until iterations of 3000. This figure show the temperature contour of our vaccine container. As you can see from the figure, there is a red, orange and blue region. This color region show the temperature contour of our vaccine container design. The maximum temperature is about 243 Kelvin, which is indicated in the red region, while the minimum temperature is about 202 Kelvin, which is indicate the blue region. From the figure, okay, we can compute that the vaccine can be placed at a lower part of the container since it has the lower temperature than the front part, which is near to the door of the container as a result of the cold air supply. Okay, then this is the inlet and outlet temperature control of our vaccine container. Okay, we can observe that the resulting color in blue region, which is the outlet, which is connected with cooling duct. Okay, this is because the cooling system airflow will pass through this part first before the cool air reach another container area. Then lastly, okay, for the velocity streamline of our vaccine container, we can observe that the air that delivers the cold air is not too quick, which is about 3.67 meters per second, okay, at the outlet, and rather uniform, allowing for more even and slow cooling. The temperature contour will be affected by the velocity of this streamline because this velocity will determine whether each container space is effectively fulfilled or not.
My name is SHARVEN and I will talk about the discussion part of our project. So the main goal of this project is to create an ultra cold refrigeration system that will allow vaccines to be transported to any point globally. The vaccine's temperature must be controlled successfully with a constant and maintained temperature of minus 70 degrees Celsius, necessitating the use of an ultra cold refrigeration equipment. According to the refrigeration system designed by our group, there are two refrigerations that will be used, which are the R404A for high temperature circuit HTC and R508B for low temperature circuit LTC. So R404A, or also known as Freon 404A, is a blended hydrofluorocarbon refrigerant comprised of R125, R134A and R143A. It was designed to replace R502 and R22 used in commercial refrigerator equipment for low and medium temperature ranges. Its properties makes it ideal for use in display cases, refrigerated vehicles, ice makers and other applications. The reason Freon 404A was chosen because it is a non-flammable, low-toxicity refrigerant that carries an Ashrae A1 safety classification and offers similar properties to the refrigerant it replaces. It has zero ozone depletion potential (ODP) and a global warming potential (GWP) of 3920. Freon 404A offers the best overall properties when compared to R502. Its capacity and efficiency values are equivalent to R502. It operates at comparable physical and thermodynamic properties, which makes transitioning to new systems or retrofitting older systems easier. The compressor discharge temperatures of Freon 404A can fall 9 degrees Celsius (14 degrees Fahrenheit) lower than R502, which may lead to longer compressor life and better lubricant stability. The another refrigerant used for low temperature circuit (LTC) is R508B. It is also called as Freon 95. Freon 95 refrigerant sets the industry standard as a replacement for R13 and R503 refrigerants and is endorsed by original equipment manufacturers (OEMs). Freon 95 ensures that medical freezers and environmental chambers can consistently maintain temperatures that range between -40 to -101 degrees Celsius. This refrigerant was chosen for LTC because of several advantages, which includes it is an Ashrae A1 classification. It is a significantly lower compressor discharge temperature versus R23, ensuring optimum system reliability for critical application. It has 30% greater cooling capacity than R13 and comparable performance characteristic to R503. And finally, it has zero ozone depletion potential (ODP). A two-stage cascade refrigeration system is used for our proposed refrigeration system. Cascade refrigeration systems can retain a high level of energy efficiency when running at low temperatures. One of the main reasons is that refrigeration takes less compressor effort than a traditional refrigeration system. Electricity consumption has been reduced by about 10% on average. To achieve exhilaratingly low temperatures, cascade refrigeration can be used as low as -120 degrees Celsius. Traditional systems have a lower coefficient of performance (COP) than cascade systems. This is due to the fact that they provide more cooling impact while requiring less compressor labor. The pressure ratio is inversely proportional to the volumetric efficiency in the refrigeration cycle. Cascade refrigeration systems have low pressure ratios as compared to standard refrigeration systems. This means that cascade refrigeration systems will have a higher volumetric efficiency, which is desirable. The importance of the cascade refrigeration system has enabled our system to achieve ultra-low temperatures. Some of the benefits when it comes to using a cascade refrigeration system includes lubricating problem will be reduced as it has to withstand temperature range not more than 60 degrees Celsius. Secondly, when compared to bigger compressors, the performance of a cascade system can be enhanced by lowering the temperature differential for heat transfer in evaporator condenser and cascade condenser. And thirdly, the power consumption of cascade system can be lowered by roughly 9.5%. In terms of transportation of vaccines, some regulation and guidelines must be followed so that the vaccines will be carried around globally in a temperature-controlled transport. For air and sea transport, it has to be ensured that any carrier contracted to transport the vaccines by air or by sea operates under the term of a formal service level agreement (SLA) drawn up by both parties. The carriers is to be made responsible for maintaining load temperature within the transport temperature profile defined for each product. This is because to ensure that the carrier is made responsible for maintaining load temperature within the transport temperature profile defined for each product, and that compliance can be demonstrated to the contracting organization, the regulatory authorities, and other interested parties.
For the conclusion, the vaccine container designed and simulated can supply a temperature range of -30 degrees and as low as -71 degrees. So this achieves our objective, which we need to maintain the vaccine temperature at a temperature of -70 degrees Celsius. So the problems that may arise is that the untight seal of the door, which can let cool air inside to escape, thus increase the vaccine temperature. So the solution for this problem is that we need to apply a rubber or silicone seal on the door linings to ensure no gaps are present. So next is that the vaccines arrangement can affect the temperature of the vaccines, which if we arrange from the back to the closest to the door, the back which is closest to the cooling duct, the closest to the cooling duct will have a lower temperature compared to the ones at the door. So this can affect the vaccine temperature can be vary from one vaccine to another vaccine. So to overcome this problem, we need to lower the temperature of the vaccine, thus lower the temperature of our vaccine container lower than the specified vaccine temperature, which is safe. So overall, all objectives were met, and this vaccine container can help the vaccine companies to safely deliver the vaccine throughout the world over any climate. So they can reuse this container through multiple times, and they can deliver it as efficient as possible.